Hi, today we will discuss flexural analysis for reinforced concrete rectangular beams. As an introduction, we learned that the stress and strain relationship for concrete and reinforcement are used to develop an understanding of the flexural behavior of rectangular beam sections. The effect of changes in material and section properties on the flexural behavior of the beam sections will be presented here. Also, after gaining a good understanding of the entire range of flexural behavior, a general procedure will be developed to evaluate the nominal flexural strength M sub n for a variety of beam sections. Also, simplifications for modeling material properties which correspond to the ECI code definitions for nominal strength will be presented. For most reinforced concrete structures, it can be divided into two, the beams and slabs and columns. Beams and slabs are subjected primarily to flexure and bending. Also, columns are subjected to axial compression and bending. You can ask, how about footing? Footing is actually primarily subjected to shear. So you can design it in terms of shear, especially the thickness. Then after that, you can design it using flexure. Here is a typical example of a flexural member coming from the top, the one-way slab where a load force P is applied at point A. This load force will be transferred towards the short direction of the slab towards point B and point C. And from point B, that is the girder or the beam, the force will be transferred towards the column at point D and point E. And then from the column towards the footing and then the foundation. There are two types of reinforced concrete problems. Normally we do analysis or design. If we say analysis, cross-section, concrete strength, reinforcement size and location, and yield strength is given, and we will compute for the resistance or strength. In the analysis, there should be one unique answer. Unlike design usually the given is the factor design moment, normally designated as M sub U. Select a suitable cross-section including the dimensions, concrete strength, reinforcement, and so on. With these given values, there are a lot of values or a range of values. Hence, the result of design is that there are many possible solutions. Just imagine if you will just say concrete strength should be 21 megapascal and you will have different dimensions. And also if you say FC prime will be 24, then that's another set of solutions. It's not just one solution, but several solutions. So that is why in design, many possible solutions will come out. And this is the reason why we usually have different sections, different strands, different dimensions, because we vary in our assumption. Also, when you're designing, you have to take note of the typical notations. Usually for rectangular sections, the dimensions is B and H. For the concrete and steel reinforcement, we usually use FC prime and FY and AC and ES. For the main reinforcement size, we use D sub B, and for lateral ties or stirrups or the transverse reinforcement size, D sub S. Also for the resistance or strength, we have P or pi M sub N. Also the factor design moment is M sub U. The basic strength requirement from the ECI NECP code is given as follows. The reduced nominal strength should always be greater than or equal to the factored load effects. Or in terms of flexure, we can just say the reduced nominal moment is P times M sub N, which is always greater than or equal to the factored load effects, that's M sub U. Again, M sub U is taken from the load combinations that we discussed earlier, and it should be compared to the reduced nominal strength. That is, we have to compute first the nominal moment, M sub N, and to be reduced by the strength reduction factor P. In the case of flexure, that's equal to 0.9. Here are different symbols and notations. You should be able to familiarize these symbols because this is very important in our design. Like for example, the capital A sub S is the tension reinforcement. If there will be prime, that is ES prime, this concerns about the compression reinforcement. Small b is a general symbol for the width of the compression zone. Take note, compression zone in a beam, because in a plan section, if the compression zone is in the plans, then your B is equal to B effective or B sub E, or it can be B sub W, that is the width of the wave. B sub E is the effective width of the compression zone for a plans section with compression in the plan. And B sub W is the width of the wave of the member. And D is the distance from the extreme fiber, take note, extreme fiber in compression, to the centroid of longitudinal reinforcement on the tension side of the member. Again, if there would be prime, it concerns about the compression reinforcement. So D prime is the distance from the compression or extreme compression fiber to the centroid of longitudinal compression steel. D sub T, on the other hand, is the distance from the extreme compression fiber to the farthest layer of tension steel, farthest layer of tension steel. So it does not coincide with the centroid of the tension steel. In that case, D is usually not equal to D sub T. But there are cases where D is equal to D sub T. That is for a single layer of tension reinforcement. Also take note that we always talk about the tension and compression. So it's very important that you will be able to discern where is the compression side of the beam or the tension side. We will talk more about it in the next slides. Other symbols are FC prime, which is the specified compressive strength of concrete, FC, the stress in the concrete, Fs, stress in the tension reinforcement, Fy, the specified yield strength of the reinforcement, H is the overall height of a beam cross section, H is different from D, but normally H is greater than D. GD is the lever arm, the distance between the resultant compressive force and the resultant tensile force. J is a dimensionless ratio used to define the lever arm, that is GD. And epsilon sub Cu is the assumed maximum usable compression strain in the concrete, and epsilon S is the strain in the tension reinforcement, epsilon T is the strain in the extreme layer of tension reinforcement, and rho is the longitudinal tension reinforcement ratio, which is defined as the tension steel ES over BD. A beam is a structural member that supports applied loads and its own weight primarily by internal moments and shears. If the axial applied load N is equal to 0, the member is referred to as a beam. But if N is not 0 and it is a compressive force, then the member is called beam column. So we will define first the concept of couple. I know you have learned about this one in your static of rigid bodies, but it's very important now that you will really understand this concept. A couple, or we call it a bending, is usually defined as capital M. It can be clockwise or counterclockwise in direction. We can actually find an equivalent of the couple in terms of a force. We can look for an equivalent force that is parallel to each other. The force with the same magnitude but in the opposite direction. And these should be parallel to each other at a distance E. So that the couple M is equal to P times A. The loads W and P below will cause a bending moment. The bending moment is a load effect calculated from the loads by using the laws of statics. So you can see this given beam. We can always look for the shear and moment diagram. In this particular diagram, we are concerned about the bending moment diagram. So at any section, you will be able to get the bending moment. Like for example, at section A, if we have to cut this section, remember what we are doing in our structural theory, we usually cut a portion of the member. We can apply the same principle by cutting at section A. We will be able to find the bending moment. At this section, the internal resisting moment M is necessary to equilibrate the bending moment. And also, aside from the internal resisting moment, we can add internal resisting shear V. Whatever the bending and the shear on the left of the section, it is also the same with the other side, but in the opposite direction, so that the other section should also be in equilibrium. It would be difficult for us if we will just be talking about the internal moment M. Normally, we want to have an equivalent force of, instead of using M, we can use the equivalent force. As we have discussed earlier, the couple M can be described in terms of the force, an equivalent force or a force of the same magnitude but in the opposite direction. Those forces in this case is what we call the resultant compressive force C and the resultant tension force T. So as you can see in the figure below, we have the corresponding tension at the bottom and the corresponding compression at the top. And also we have the shear V in one side and on the other side. Also remember that there is a distance between C and T, that is GT. So that the couple M or the bending moment M is equivalent to C times GT or T times GT. Actually, they are the same, even if you have to sum up anywhere at any point. But the most simplified way of summing up moment is at the compressive force C or at the tension force T. By summing up moment at C, the moment is simply equal to T times GD, or summing up moment at T, C times GT is also the bending. So they are equal actually. Also, it's very important that you will be able to discern the location of the tension and compression side of the beam, because this is very important in positioning the reinforcement. In particular for a T-beam, like for example this one, for the positive moment, that is compression on top and tension at the bottom, this is usually located at midspan. So at midspan of the T-beam, most of the tension reinforcement is located at the bottom, and the compression reinforcement will be located in the compression zone, that is in the flange section. With respect to the support of a T-beam, if this continuous beam is different, the moment is negative at the supports. So in that case, if it is negative, then the tension side is located at the top or at the flange, and the compression side is located at the bottom. So as you can see, I use different colors for the tension reinforcement and compression reinforcement so that it would be easy for you to discern the location of the tension and compression. Aside from this, we can also learn more of the location of the tension and compression. This is very important. Of course, I assume that you have learned this one in your structural theory. This is what you are discussing actually in your structural theory, looking for the tension and compression, but maybe you were not able to easily discern it. It's very important that you have to review your structural theory. You can draw the shear and the moment diagram, and then after the moment diagram, according to that sign of the moment diagram, you will be able to draw the elastic curve. It's very important that for a positive moment, the elastic curve should be concave upward, and for negative moment, the elastic curve should be concave downward. If we have to use that principle here for a simple beam, like for example, if you have to apply force at the middle, then your beam will bend downward. You don't need any moment diagram here. It's logical that the beam will bend downward. Okay, so the curve should be concave upward, but you can also check this one by drawing your moment diagram. Your moment diagram for a simple beam will be positive, so the elastic curve should be concave upward. But for a fixed ended beam, that would be different, because you have use a fixed support at both sides, then moment diagram will change. Here, it's very important to know the moment diagram, because by just looking at the figure, it would be difficult for you to discern the curvature or the elastic curve. So you can use the moment diagram. You will notice in your structural theory, at the supports, the moments are negative, and at the midspan, the moments are positive. Meaning, if it is negative moment, then the curvature should be concave downward. So both supports should be concave downward and the midspan concave upward. What does it mean? The tension at the midspan should be at the bottom and compression is the top, but at the supports, the tension should be at the top and compression should be at the bottom. So as you can see, I use different notations, two notations, T for tension and C for compression. For the cantilever beam loaded this way, first the tension will be at the top, compression at the bottom. And then for an overhanging beam, as you can see for this particular loading, the tension should also be at the top. You can also look for other structures. These are just quite simple structures just to give you the idea on how to locate the tension and compression, so that when you are designing, especially for reinforced concrete, you will be able to know the tension side and the compression side of the member. Okay, so that's all for now. We will continue our discussion in the next bit. Thank you for listening.